We're going to be learning about circles today, and we're going to start off with a pretty basic question of how do we know whether a point is inside, outside, or on a circle? And it might seem like an obvious question, like I could draw a point over here and you'd say that that's outside the circle, right? But the closer and closer we get to this line, it becomes pretty uncertain. Maybe we get like a femtometer or something close to this circle, which is really tiny. And it gets pretty hard to tell whether we're on the circle or outside or inside. So do you guys have any ideas of how we could know for sure whether our circle was inside, outside, or on the circle? Did I say circle on the circle? Point on the circle? If you need a hint, we can compare, say we knew what the radius was, maybe this is like 8 inches or something. If we knew the distance from the center of the circle to the point we drew, would you guys be able to make a guess at how we can know?
Maybe.
Let's say from the center of our circle to this point, it's 10 inches.
So we know that it's outside of the circle because it's further away than the radius?
Yeah, exactly. The distance from that point to the center is larger than the radius. So what could you say about a point that was inside the circle?
Maybe less than
Less than.
Awesome. And then on the circle too?
Equivalent to 8.
Exactly. And that might seem like it's pretty pointless, but it's kind of important for math to have a precise definition that we could use later. It'll be really important for this proof we're going to do later. But we can explore some properties of these points. Like, say we have a point inside the circle and we want to draw a line through it that extends infinitely long. It would have to hit 2 points on that circle, right? I don't think there's any way we can get around it. No matter how we tilt this line, it would have to intersect the circle at 2 points. And this is called a chord with a silent H. This is something we'll be exploring later in the unit, but there's some other things that we could see too with the different properties. If we chose a point on the circle and drew a line through it, we could have that line intersect twice again and form another chord. Or we could have the line just barely touch it at the edge of the circle and keep going and only intersect it once. And that's actually going to be the topic of today's conversation. They're called tangents. And tangents are defined by lines that only intersect circles once at this very specific point. And what we're going to be proving today is that if we draw the radius of a circle, say we have the radius is AB, and we have this line L, we want to prove that our lines are perpendicular here. And this is going to be going back to some prior knowledge that some of the students in my class would have known from lesson 1 at the beginning of the year. It would have been some proof writing and logical skills and everything. I imagine even they'd be a little bit rusty on it because it's hard to remember things from months ago. But we're basically going to be doing a proof by contradiction, because right now we don't really have anything to go on. If we want to figure out that this is a right triangle, I mean, we can't really draw any lines that would really help us here. So the only thing that we could do, I mean, we can't do a direct proof, so we have to do a indirect proof, or a proof by contradiction. So our first step that we'd want to do here is assume that this isn't a right angle. We could say assume angle, we can say B, is not right. Now, if we're saying that this angle isn't right, would you guys agree? It's kind of a trick question, right? If a teacher asks if you're going to agree with them. do you guys think that there has to be some line that goes through the center of the circle that has to make a right angle with line L at some point?
Yeah.
Yeah. So I'm going to say that there's some line that goes through point A and hits point L. I'm going to say let's call that point C. And I'm going to say that that is the point where we have a right triangle. And this is a lot of times where people will say, that can't be a right triangle. It doesn't look like it is, right? And it gets back to, we got to look at what we know and what we're assuming rather than what the picture looks like. Just like earlier when we said we might have a point that's super close to the edge of the circle and might not look like it's outside or inside the circle. It might be on the circle, but we don't really know by the picture. So we're saying that angle C is a right angle. Now we can do something with right triangles. If you guys thought of right triangles, what would probably be the first thing that popped into your head? If you're trying to find maybe like the hypotenuse or something.
Like the Pythagorean.
Yeah, exactly. Do you remember what that is?
A squared plus b squared equals c squared.
Exactly. So if we're going to label these sides, typically people do A, B on the legs, and C is the hypotenuse. We could say that A squared plus B squared is equal to C squared. By the way, this point AB is the radius, right? That's going to be kind of important to note for later, so I'm just going to put that bit of information down right now. Another thing we know about right triangles is that the hypotenuse is the longest side, right? If you have a squared plus b squared is equal to the single side c squared, then c has to be the longest. So, right now, we're assuming that c is longer than a, right? If a leg of a triangle has to be shorter than the hypotenuse, then line AC is greater than AB. Now this is going to go back to what we learned at the beginning of the class of how we know a point is inside or outside of circle. If we know that AB is longer than AC, then what do we know about point C? Kind of ignoring what the picture looks like.
It would be shorter.
Yeah, it's shorter. So even though the picture looks like C is on the outside of the circle, where is C actually?
Inside of the circle.
Exactly. So if C is inside the circle, maybe we could make a little new reference here. How many times would a line going through C have to intersect the circle?
Twice.
Awesome. So we know L intersects circle A twice. Don't you guys have a problem with that? Is that kind of weird? I mean, this whole thing, we started off with this whole proof just knowing that L was tangent to the circle, right? And what was the definition of a tangent line again?
It only touched the circle.
It only touches once, so we kind of have a problem. And where did this whole mess start? I mean, we had to make an assumption at the beginning, right?
The angle B is not right.
So I guess if we hadn't assumed this, we wouldn't have gotten that L intersects twice. So I guess the only thing that could logically be true is that our assumption was wrong, and that angle B is actually a right angle. And now we know for sure that if you have a tangent line to a circle, there has to be some radius line that's perpendicular to it. And then what we're going to be working on for the rest of the class is we're going to be proving the opposite. If we had some radius here and we knew that it was tangent to a line, would we know that it's the tangent? Or if we had a radius and it was perpendicular to a line here, could we prove that's the tangent? The answer is yes, but we're going to be working on that a little bit. But that's kind of going into the student-led discussion and everything, so I'm just going to call it quits here. That's it. That was my time.